So I was watching this YouTube video, which I can't find anymore, and saw this really cool animated background. I thought, hey, I can probably make something like that. So I did, and this is how you can make one too in the Godot game engine. Let's start by configuring the project settings. Set the window stretch to 2D, and the environment clear color to black. For the base scene, we create a new 2D node and name it Poly Background. Giving the project a quick run, everything is functioning, although not that exciting. Next, let's create another scene of type Area 2D. Call it the creatively named Dot, and add the required collision shape node. We choose its shape to be a circle and use a radius of 50 units. Next up, let's add a script to the scene and give it the class name Dot. We'll start by adding two export variables, velocity of type vector2, and speed that we will default to 30 units. Now we'll delete the ready method as we don't need it, and add a new function called initRand. The first parameter will be a random number generator, and the second a vector2 called screenExtents. The first objective of this function is to randomly choose a position for the dot somewhere on the screen. The screenExtents variable defines the screen size, so we simply need to generate a number between the bounds. The random number generator variable can generate a pseudo-random floating point number in the range from 0 to 1. To map 0, 1 to a larger range, we can simply multiply the max value by the result. So a value of 0 will map to 0, and a value of 1 will map to the max value of everything in between. However, this only works if the min value is 0. To use a min value other than 0, we need to first shift the range back to 0, multiply by a random value, then shift back. In general, the formula is max minus min times a random value plus min. Our min value is minus extents, and our max value is positive extents. So simplifying the equation, we get extents times 2 times rand minus extents. See kids, the math we learn in school does have a use, like randomly drawing dots on a screen. Coming back to our code, we will write this formula out for both x and y. Finally, we construct our position vector using both values. For the velocity vector, we simply use the rand value from 0 to 1 for both components. For now, we move back to the base scene and add the camera child node. Make sure to set current to true. Next, we create a new script. In it, we will define two export variables, rseed set to 0 and num.dot set to 50. In the ready function, we create a new random number generator and set the seed to rseed. For context, in computing, true random numbers are tricky, so we typically use pseudo-random generators. These objects create a series of numbers that look random enough for humans, but aren't truly random. These objects are configured using a value called a seed. Each seed will create a unique series of random outputs, but the same seed will always create the same series of outputs. Back in our code, by setting the seed explicitly, we can ensure the generated dots will always be the same as long as we use the same seed. Next, we iterate for every dot and create a new instance of the dot scene. We call the initRand function and pass in our generator. For the screenExtents, we can grab a camera from the scene tree, get its viewport, and finally its size. Size defines the whole rectangle, so we divide by 2 to get the extents. Lastly, we add the dot as a child scene. Running the project at this point still won't show anything, since we haven't added any render code to the dots, but if we inspect the live scene tree, we can see that 50 dots have been added. To add render code, we move back to the dot scene and implement the draw method. Here we make a simple call to draw a circle and pass in the position, radius, and color. Note we use the origin as the position, as we are drawing in local space relative to the dot scene. The position variable is the position of the entire scene relative to its parent. This can get a bit confusing and did create a hard to find bug in my practice code. Running the code at this point, we can see that indeed 50 dots are positioned randomly across the screen. I didn't count them, but feel free to pause and verify. Note that when we change the seed value from 0 to 1, we get an entirely new distribution of dots, proving our generator is working. Moving on, let's make the dots actually move. In the dot scene, we implement the process function, which is called every frame, and the parameter delta is the amount of time passed since the last frame in seconds. In the function body, we increment the position by the velocity, which describes the dot's direction, multiplied by the speed constant, and finally delta. Lastly, we need to call update to tell the engine to re-render the frame. Technically, this isn't required yet, but we will need it later, so I add it now for convenience. Running the project, we can see that the dots are now moving in different speeds in different directions. This is thanks to our velocity code from earlier. However, having the dots just poof out of existence after leaving the screen isn't very exciting, so let's get them to wrap to the other side of the screen. Back in the base scene, we add an area 2D node, renaming it the play area, and add its required collision shape. We choose a rectangle shape this time and expand the extents to the size of the viewport. Next, we're going to connect the area exited signal. Firstly, we need the extents of the player area, which we can get from the collision shape as such. Now, even though our camera viewport code still technically works, it would make more sense to use the player area extents in the rand function. To achieve this, we create a new helper function that returns a vector2, and paste the extents code. Now we can simply call this function in the ready method, and the area exited method. Now the screen wrapping logic itself is a little convoluted. Basically, the exited signal will fire when the dot's collision circle exits the play area. At this point, we want to warp it to the other side of the screen. The exact position is the opposite side of the extents, plus however far out the dot was past the extents. This distance can be calculated as position minus extents when the position is positive, and position plus extents when the position is negative. Note this second distance will be negative, so we also need to take the absolute value. In code, these equations look like the following. Like I said, quite convoluted. Although maybe there are a few simplifications, this was the best I could come up with. Running the code, it does appear to be working, although it's kind of hard to tell since the dots spend some time off screen before warping. To get a better sense of what's going on, we can zoom the camera out a bit. Now it's much easier to see that it is indeed working. Okay, so we've been staring at a bunch of white pixels for far too long. Let's finally make it a bit more interesting. Back again in the dot scene, we add a new variable called nearby dots and initialize it to the empty array. We next bind both the area entered and area exited signals. In these functions, we simply add the area to the list when entering and erase the area when exiting. However, we should be careful that we are only adding dots to the array. To achieve this, we simply add an instance check to both functions. However, in Godot, you cannot reference the class name in the same script else you create a cyclic dependency, so we can use the getScript method to bypass this restriction. Running this time and no errors. Next, we're going to add a fair bit of code to the draw function, so for ADHD's sake, I'm going to move it below the process function. First, we iterate for every nearby dot and draw a line between the pair. This line goes from the origin to the other dot with the color white and a thickness of 2. However, remember this is local space, so we need to first convert the other position to local space using this handy function. Running the code, we are starting to get somewhere. Lines will appear as two dots get close and disappear when they drift apart. However, it doesn't look very good yet with some interesting issues, so let's amend that. First, let's add a new variable for the converted position. Now, a small optimization we can employ here is only drawing the line half the way to the other dot. The other half will be drawn by the other dot during its draw call. Next, we also create a new variable for the color. We adjust its alpha channel, i.e. its transparency, based on how close the dots are to each other. We'll calculate the distance to the other dot, and divide that by the max distance, which is twice the collision radius. This will give us an alpha of 0 when the dots are on top of each other, and a value of 1 when they are at their max distance. However, we want this to be the other way around, so we can simply invert it by subtracting it from 1. Running once more, and things are really starting to take shape, pun intended. Now instead of popping in and out of existence, lines fade in and out satisfyingly. I also think that differing transparencies creates illusion of depth, which is an awesome bonus. Although we do still need to fix that weird render issue caused by the screen wrapping, which is way more apparent if we comment out the alpha code. To address this, we will move the distance and max distances calculations into variables. Next, we do a simple sanity check to see if the distance is greater than the max distance. If it is, we continue, which will skip the rest of this iteration, or at least when you spell it correctly. Finally, we repair our effort code, fix some syntax issues, and run again. With alpha fade disabled, we can see that the issue has been rectified. After re-enabling alpha fade, the scene is now complete. Although it is still a little underwhelming, so let's increase the number of dots from 50 to 80. Now we're getting some much more interesting shapes. Additionally, we can change the seed to get a totally different pattern. And believe it or not, that's everything. Quite the satisfying result for so little code. In total, less than 100 lines, including some white space. Most programmers like to brag about how many lines of code their projects are, but in my mind, doing more with less is just as impressive. Code smart, not hard.